Just let me know whether the screen is visible or not.
Yes, sir, it is visible.
Good evening, all. So I welcome you all to this week 11 live session on NPTEL course of deep learning. So this course is provided by Professor Praveen Kumar Desai, who is a professor in the Department of Electronics and Electrical Communication Engineering, IIT Kharagpur. So in this particular live session, we'll actually first solve the quiz 10, and followed by that, we'll take up some problem, basically the practice problems for week 11 content. So in week 11, we have seen some of the concepts like uh, we have seen a new variety of loss function, that is uh, ex- select these things first. So we have seen a new type of loss function, that is triplet loss. Along with that, we also have seen a new type of uh, learning mechanism, that is called one-shot learning. And along with that, we also have seen a new variety of problem, that is called semantic segmentation, basically an image segmentation problem. So it could be instance segmentation, semantic segmentation. Majorly, we'll be talking about semantic segmentation in this particular course. Okay. So another reminder, probably you've seen, I think someone's mic is on. Yeah, so that reminder is that please turn off your mic. I hope you have seen that that week 8 question, week 8 question number 9, where the correct answer would be softmax, but it was counted as leaky ReLU. So this particular anomaly has been corrected currently in the website. So you guys just can go to the website and check your progress of the week 8 quiz. So re-evaluation have been done already. So you can see that whether your marks has been increased or not, if you have chosen softmax as the correct option. So this is just a reminder, just check whether you can see that the updated marks are there or not for week 8 question 9. And in the last class, there was another anomaly regarding the high learning rate and low learning rate. So that particular question also, I have raised an issue over there with the NPTEL quiz team. So whenever they just revert back to me, I will let you know that what is the update regarding that particular question. Okay, so let's dive into week 10 quiz. So the first question, it states that which of the following is false regarding batch normalization. So in week 10, we have seen a huge elaboration of batch normalization, the mathematical processes behind it, the gradient calculation regarding batch normalization. We have seen all those things. So let us just scan through the options. So the first option is batch normalization prevents problem of exploding. Okay. So batch normalization prevents the problem. So exploding. So by exploding, what they basically mean is basically exploding gradient. So we have seen that in case of any deep learning or any neural network architecture, there could be two scenarios with the gradient basically. So one is vanishing gradient, vanishing gradient. In case of vanishing gradient, we have seen that the del WL of W, it almost becomes zero, and therefore your learning basically gets stopped over there. So what happens is Wn plus 1, if we just mathematically see what happens over here is Wn plus 1 becomes W of n, as because eta multiplied with del W of LW, it becomes zero, and therefore this term vanishes, and therefore you can see that your learning mechanism, that what you've been doing using backpropagation method, so that has been stopped. So effectively your learning is stopped using at the time of vanishing gradient. Now the another problem that is there in case of any deep learning network that you might encounter over there, that is called an exploding gradient. Exploding gradient. So all these concepts have already been discussed in probably week 8 or something. In week 8, wherever the gradient topic was covered, so over there, Professor PKB has described what is vanishing gradient, exploding gradient. So in case of exploding gradient, what happens is that your gradient value becomes excessively large. So it becomes very high value and very, sorry, and very high value. Let us consider uh, it is in case of Python, let's say you might encounter a error that is called INF or infinite value error. So over there, if your gradient becomes very high, let's say you are getting very high value such as infinite. So over there, you can see that your mathematical expression will no longer be giving you the result, because you will encounter either INF or NAN, that is not a number error. These two cases you might encounter. So to reduce this vanishing gradient, we have seen that what are the methods? They are basically regularization, regularization, then dropout method. Uh, Along with that, you can actually another remedy could be early stopping. So early stopping, it basically helps to reduce overfitting, and overfitting has some relation with this vanishing gradient. That means you might be doing well with the what you call in the training set, but might be not doing well with the validation set over there. So, regularization, dropout, these are the methods by which you can actually do some, you can take measures regarding vanishing gradient. Now, what about exploding gradient? Now you can see that you are getting a very high value over there. It might not be, let's say, it might not be infinite or none. Let's say it may be 100 million over there. So in case of LW, so you know that from all previous lectures that in case of deep learning or machine learning techniques, we deal with the matrix, we deal with different variety of matrices. As long as let's say you are dealing with a neural network architecture like this, so whenever you have to actually do the back propagation over here, you need to think about all the weight values. Now all the weight values can be stored in a matrix or an array, and you need to update that particular time. So wherever you will be doing any kind of this back propagation application or any neural network application, whatever data type that you will be dealing with, that is basically a matrix or an array. It could be tensor as well if you are dealing with high dimensional data. Let me just restrict myself. Yeah, Anurag, are you saying something? I just muted you. So,
No, sir,
uh,
not.
okay, fine. So over here, whenever you be dealing with any sort of neural network architecture, basically what you are doing some sort of matrix manipulation over there. Now, you can see that, let's say in a matrix or an array, for example, over here you have very high value n high, and let's say you have moderate values and low values as well. So let's say n low. So due to this particular n high or the high value, you have seen that as because this is reaching very high value, so over here you might be getting error, that is infinite error or nan error. So how we can drop down? So what we have to do in case of exploding gradient? So this high value we have to brought down to relatively low value. So how do we do? How do we brought down this high value to a relatively low value? So this we can do using the concept of normalization. So in case of normalization, what you will do is, for example, one sort of normalization technique would be you just divide with the maximum value. So over here, maximum value is n high only. So you divide it with n high divided by n high. So likewise, all the values will be divided with n high. So likewise, n low will be n divided with n high. So over here, you can see that whatever high value was there, now that value is mapped to a strict boundary, that is 1. And over here, this value will also be approximately reaching to 0 or very low. It will be, you can understand that already this value is low. You are dividing this particular value with a very high value. So over there, the output of this particular division will be very low, which is approximately, let us consider 0. So over here, you can see that the high value is now mapped into a restricted range of values, which ranging from 0 to 1. So now you can understand that in case of exploding gradient, if you have very high value, you just have to normalize that particular value so that your gradient value becomes bounded. So over here, the remedy is normalization technique. And one such normalization technique we have seen in case of the week 10 lecture, that batch normalization is one such efficient normalization technique which we use in deep learning architecture. So it basically helps in exploding, preventing the exploding gradient. So the illustration is over here. So in case of exploding gradient, you get a very high value. You need to normalize that particular value, and you can normalize that value using batch normalization technique. So over here, option A is a true option. Uh, Now let us first see option C. So option C states that batch normalization may prevent covariate shift. So in the normalization lecture series, before the starting going into the nitty-gritty information about batch normalization, layer normalization, and all, we have seen phenomena that is called covariate shift. So in case of covariate shift, what happens is that if you, for example, this is training batch 1, so TRV1, and let's say this is TRV2. So over there, let's say you have two classes. One is flower and one is any class other than flower. So let it be other than flower. So it can contain anything. Let's say a picture of Taj Mahal, a picture of dog, anything. So over there, let's say in case of training batch 1, you have a red color flower. And in case of training batch 2, let's say you have a yellowish flower. So now you can see that within uh, these two batches, as the batches are differing with the type of data that you are feeding into the deep learning model. So over here, you can see that color informations in both these batches are different, and hence their probability distribution will also be different. And when your model will actually try to map it into the latent space, so over there in for some batches, you might see that the flowers are mapped over here and non-flowers are, let's say, mapped over here. So your decision boundary might be like this. However, in this particular case, as you can see that as the data distribution is quite different, which was there in case of TRB1, over there the color of the image was red and here you can see the color of the image is yellow. So you might encounter classification scenario, which might look like this. Over here, the flowers are now clustered over here, just on the right, on the opposite side, which was there in case of TRV1. And let's say your uh, other than flower class is still, let's say, over here. So for this particular case, your decision boundary may be like this. Somewhere it may be like this also. For example, in some cases, let's say in TR batch 3, we have another batch. So over there, it is like this. So the decision boundary in TR batch 3 is like this. So you can see that with each of the batch, if you feed, so this is TRB1, this is TRB2, and let's say we have another scenario, training batch 3, where the other class has been actually mapped over here. So as we can see from these three scenarios that every time whenever you feed a new batch to your model is now creating different hyperplanes or separating planes to separate out these classes. And the model has to hop around. So this operation is called hop arounding the decision surface. So as the model has to hop around different sort of decision surfaces that you can see over here from 1, 2, and 3. Now the model uh, has to go through a process that is called covariate shift. So that means due to variation in the input image signals itself, your decision boundaries are now shifting based on the data that you are feeding to the model. So this introduces a phenomena that is called covariate shift, where the model has to just hop around different sort of decision boundaries. So to prevent this covariate shift, what we have to do is, as because you can see the data distribution is different, so we need to employ uh, normalization technique. So that normalization is a z-score based normalization. So where we just take x minus mu by sigma, and based on how you calculate this mu and sigma, you have different sort of normalization techniques. Let it be a batch normalization, layer normalization, instance normalization, whatever it may be. But the main target is basically to reduce this phenomena that is called the covariate shift. So over here, batch normalization actually tries to prevent the covariate shift. So option C is also a true option. So option A was also true. So as we can see that option A and C are true, so option D is also nullified. So you don't have to think about it. So option A, C, D is nullified. Now we need to see that what whether option B is a false option or not. Anyway, you can now just by using nullification, you can see that option A, option B is left. So option B will be the correct answer, but we need to see that what is the reasoning behind it. Okay. So there are two things that you have to consider when you do batch normalization technique. So batch normalization technique, it basically calculates the mean and standard deviation using two different techniques. So they calculate these two statistics in two different methods. So one method is that they follow in training phase, and in testing phase they follow different uh, method to calculate the mean and standard deviation. And what are those basically techniques that they follow? In case of training, uh, training phase calculation. So in case of training, what you have is basically, let me just go to another slide over there I have shown the. So just tell me whether what sort of normalization is happening over here in this particular image. In this particular image, what sort of normalization is happening?
Batch
Is that,
normalized.
yeah, so over here, batch normalization is happening. So let me just, this is batch normalization. So in case of batch normalization, you have, for example, you feed different pictures into the model, you get these tensors. So these are the tensor outputs basically. Now these tensor outputs, what you have to do, you have to accumulate the channels first and then you have to start doing the normalization process. So over here you can see that you are extracting channel 0 from each of the uh, tensor outputs. Then you are accumulating them. Then what you do, you calculate the mu and sigma based on the statistics based on the channel accumulation. So over here, you are basically normalizing based on the spatial dimension. Spatial dimension means the height and width of these tensors. So it is basically if this is the height h, let's say this is height and this is width of the tensor. So this is height and width. So this is called the spatial dimension. So you are actually taking the actually calculating mu and sigma based on the spatial dimension and the batch across basically across the batch information. So over here that you can see, so N is the batch size, C is the channel number. So channel number means how many channel you have. So over here you have 0, 1, 2, 3, 4, 5. So over here you have total 5 channels. So this is channel number. This is the width of the uh, output tensor and this is the height of the output tensor. So over here you can see that let us just scan through this mu value. So this mu value you can see that you just take a particular uh, image or a particular tensor. So let us consider this is X. Let's say this is batch. This is from the first batch. So I'm taking a variable. I'm taking a running variable over here. Then you can see that you are fixing the channel. So all the channel 0 is accumulated over here. So the channel information is not changing. So that is why you can see that you are not taking any running variable over here as because the channel is constant. So C is constant. Then you have to calculate, add all the values around across the spatial width, that is spatial width and height, that is W and H. So that is why we are taking another variables, so that is J and K. So you can understand that how this XICJK has been written over here. And how many number of batch you have considered, so that batch is N. And what is the highest value of width, so that we have written over here, that is W, and height is H. So you can see that you are taking average. So this is basically you are calculating the mean. So effectively you are taking average value over here. So you are adding all the values across this particular channel, then you sum up all the information across this batch, and then you just divide with this factor N into W into H, so as you are calculating sigma over here. So these all calculations are basically the uh, training mean and variance extraction process. Extraction. So this formula, whatever you have seen over here, so these formula the batch normalization uses at the time of training. They do not use this particular formula at the time of testing. Why is it so? let me just give you an intuition over here. For example, you have a data set. You have a data set of, let's say, 256 samples are there in that particular data set. Now, let's say, uh, let me make it even easier. Let's say you have 10,000 samples. Now you take 9,000 samples or 9,000 samples in training and 1,000 samples for testing. And let's say your batch size is 10. So how many batches will be there? If you have a batch size of 10, so how many such batches will be there? Sorry,
900 and 100, sir.
yeah.
900 for training.
Yeah, so you can see that there will be 900 such batches, and in each batch there will be 10 images. So that is how you will get the whole batch that has been constructed over there. Now, uh, in case of testing phase, again, you can do the same thing. You can take the batch size as 10. So over there, it will be 100 such batches will be there that you can feed into a trained model. After training that model, you can feed those data into the trained model. Now you can see that, let's say this is the neural network architecture. You feed batch 1. So as you can see that in batch 1, there might be, let's say, you have a class of image that is flower and another one is dog. Now these flowers are of different variety. So blue colored flower, pink colored flower, red, and let's say green. Now you can see, let's say you feed a chunk of these two type of data into batch 1. So this goes as batch 1. Now, as you can see that your data looks different as because these colored informations are different. So for this particular batch, whatever new batch 1 and sigma batch 1 you will be calculating, that is different. Now let us consider you are creating batch 2 out of these two type of data, and you are feeding that into the deep learning model for training process. And again, you are calculating the mu and sigma for this batch 2. So over there, let's say mu2 and sigma 2. And at the time of training, you are basically trying to optimize that network based on there are two parameters. In case of batch normalization, we have seen that it is scaling and shifting parameters. So those are the hyperparameters of the batch normalization technique. So as you can see, as these batches are differing, so as this mu1 and sigma1 values will also differ, as because these images that with which you are constructing these batches, as they are different, so therefore their statistics will also be different. And so as you can see that there will be variation in mu1 and mu2, there will be variation in sigma1 and sigma2, and this is valid for all the batches. Now, uh, in case of testing, if you get, let's say, some new type of image data, let's say some new type of flower image data, and that flower image data, let's say it is uh, of this nature, of yellowish nature. So if you take the mu and sigma at the time of testing, so that is why I'm annotating with subscript t, small t. So this testing value, if you do based on the same equation that you had used in case of training phase. So that would create a mismatch. Why? It is because you are getting a new sort of data. Now the statistics is totally different, which was there in case of the original training data set. So to retain the information of training, because training is reference. If you have a deep learning problem, first what you do, you train your model with the training data. Now that training is a reference to you, and whatever training objectives that you have performed, let's say it could be an accuracy measurement perform, it could be MSE measurement perform. So whatever measurement you have done, based on your training scheme, if you have done very good classification in case of in the training phase, that means let's say you are getting 95% accuracy. So that trained weights are basically your reference that you will be using at the time of testing. Now all the statistics that were there in case of training, that has been captured using all this batch normalization technique. Now what you have to do, you cannot use these kind of formulas again for the test set, because now the test set, if the test set has some sort of different looking image over here, now your mu and sigma will highly differ from what your neural network have seen previous. So what they basically do is, in case of testing mechanism, in case of testing, to reduce this particular problem, that if you have new sort of data, the mu and sigma will purely vary from these mu and sigma that you have extracted in the time of training. So you need to use the information of mu and sigma that you have extracted in the training phase only. So you have to take, what you basically do, you take average of all the mu and sigma evaluated in the training phase. And those mu and sigma you use at the time of testing. So whatever mu and sigma for all the batches that you have calculated in case of training, that you basically use as an average in the testing phase, and those average mu and sigma values you basically use at the time of testing. So therefore, the type of statistics you get over here in case of training and in case of testing, they basically differ from the equation, because in case of training you have a finite equation over here. For every batch you do this particular mathematical operation to calculate the mu and sigma. However, at the time of testing, whatever mu and sigma you have extracted from each of the batches, say batch 1, batch 2, let's say till batch 10, you just take an average of those statistics. So you will get an average value starting based on mu 1 dot to mu 10. You take an average value, and that average value you use at the time of testing. So mu average is equals to mu t. And similarly, sigma average will be equal to sigma t. So this is why I just elaborated that in case of batch normalization, there are two type of techniques that they use to calculate this mu and sigma. At the time of training, you have these equations. However, at the time of testing, whatever the mu sigma you have calculated from each of the batches, you just take an average, and that you use at the time of testing to refer it to the statistic of the data. So now let us see what option B was telling us. So in case of option B, the statement is, for an input X, batch normalization produces same output regardless in the training mode or the inference or test mode. So that is false, because we have seen that in case of training mechanism, as because this mu and sigma computation techniques are totally different. So this output X hat, which is there in case of training, will not be equal to the testing, because in case of input and output, this mu and sigma extraction process will be different, and therefore this mu and sigma value will be different, and therefore this X hat, what you get in training and testing, those will also be different. So therefore option B is the false statement over here. So option B is the correct option. So if you have any query, then I can answer, otherwise I will proceed with the next question.
Yes.
Do you have any question? Otherwise, I will proceed.
Yes. Yes. Is there any way using which we can design optimal set of matches so that the variation in mu, for example, in the example you gave, we have 900 train matches, right? So we will be having mu1 to mu900 and sigma1 to sigma9.
Yes.
So is there any way we can select those matches in a way that the variation in mu1 is less?
So as of now, probably in case of one-shot learning, there is a process, or there is another new technique has come that is called contrastive learning. So there you use some sort of sampling process. So that is what you are saying, that can we create those batches in an optimal process. So let's say you have uh, uh, you have three different sets, that is anchor, positive and negative. So there could be three different scenarios. I think you have also seen these scenarios, that is easy triplet, then semi hard triplet and hard triplet. So there are three cases could be there. So this I am referring to that paper face net. So some new modifications has also came, as because this is just a foundational course. I'm not going into the details about the new paper. So in that particular paper, they showed that there could be three different scenarios. So for example, from a whole data set, from that 9,000 training data, you can create n different permutation combinations of batch creation. So you can, let's say you can take image number 1, image number 1,000, image number 9,000 over there. And likewise, you can do n sort of permutation combinations. Now,
Yes.
uh, to and if you do any sort of permutation combination, let's say you may get some cases, let's say you may get most of the cases which are hard triplet. So in case of hard triplet, what happens is basically, if I just tell you the summary, it is very difficult to classify. So uh, to reduce, so for example, if you create these type of batches, now you can understand, if you feed these sort of data into a deep learning model or neural network architecture, it is very difficult for that model to classify those sort of images. So that means your batch that you have created, that is not efficient one. You could have done some sort of modification that could lead you to create a new sort of batch. Maybe you get most of the images, let's say initially you chose 900 and let's say 1,000 as the three positive anchor and negative image. Let's say you do some sort of manipulation. In case of in the first case, it was a hard triplet, and that is very difficult to classify. Now you do some sort of manipulation while creating these batches, and you let's say get two, let's say 500 and let's say 10,000, let's say 8,000. So these are the image indexes I'm talking about: image number 2, image number 500 and image number 800. Now you see that in this particular case you may get a easy triplet set, and a easy triplet set is very easy to classify using a deep learning model. So for this particular operation, to select the to select the images to create the batches. So for that, one new mechanism that has came, that is basically label guided. So you can check this particular mathematical operation is there, that is label guided contrastive set creation. So in this particular case, what happens is that you have some sort of mathematical equations which basically helps you to choose your own optimal set of batches, which basically might help you in classification process, which might help you to do the optimization process in a much smoother way, rather than if you choose a hard triplet, the optimization process or the gradient descent operation would be very difficult to converge, and therefore you might not able to learn anything from those particular data. So this paper is, you can get this paper, is named as CLR. So I'm not going into the details about this paper, because otherwise I will not be able to cover the question. So for your reference, you can see this particular paper. In this particular paper, they have gave some notion about selecting this P, A, and N such that your classification process will be much easier. So its previous paper, what they have used, they randomly created the batches or the sets, and therefore in that particular scenario they saw that, as because we are doing random batch selection or random image set creation, majority of the cases they encounter hard triplet is coming into the picture. So in case of CLR, they proposed a new technique that is basically now named as contrastive learning. So they told a new way to select the images in such a way that your batch is now efficient enough to do good classification. So you can create the batches as per your requirement. So there are some techniques are there. So you can refer to this particular paper. I hope this answers the question.
Yes, thank you, sir.
This paper is in archive, so you can download at your terminal as well. You don't have to get to access in IEEE and other, because this is publicly available. This paper is publicly available.
Okay, sir. Thank you.
So the next question, we have seen similar type of question in the last week's live session. So in this question, the neural network has three different batches, and over there you got these activations as an output, and you need to calculate the mean using batch normalization technique. In case of batch normalization technique, we know that we first accumulate the channel information. So as because this is a vector, there is no tensor representation. So we can consider that this is channel 1, this is channel 2, and this is this is channel 1. So all these are basically channel 1 output activation. So these are the channel 2, and these are channel 3. So what we have to do, we have to first accumulate all the values, and then we have to calculate the mean. So over there, the process would be, we are accumulating over here 4 plus 0 plus 8, and now divided by 3, and similarly 4 plus 2 plus 9 divided by 3 over here, and 3 plus 5 plus 1 divided by 3. So it is 3, is 4, and it is 5. So you get this particular answer. This is pretty easy. I hope there's no
Sir,
confusion.
one question.
Yeah.
Would the neuron which are given here, would it be in the same format, like three by one? Can it also be 1 by 3 shape?
Yeah, it can be 1 by 3, because let me just whenever let's say you are, it is a vector. First of all, it's a vector. Let's say A. Let me just write the first one, 4, 4, 3. So you are doing all these operations in a matrix or in a array based operations you are doing in case of this deep learning, machine learning problems. And if you have three-dimensional or more higher dimensional data, so you will be again doing the matrix operation, but that time we call it tensor operations. Now, this A vector that you are seeing over here, you can write it as 4, 4, 3. That you are asking, right? You can write whether you can write it in 1 cross 3 format or not.
That's right, sir.
Yeah, so you can do it. there is no harm in this, because there what you have to do is you just take and transpose over there, because if you start doing the coding session by yourself, you will see in case of NumPy, basically as in deep learning models, you are doing the matrix operations. So we have seen in many of the cases, W transpose X we write. In many places we have seen that W transpose X we write. You may change your equation and you may construct everything such a way that generally in case of deep learning, we prefer to write with column vectors. That is what written over here. Now, if you choose to be your data in row vector format, then this particular format will change to X transpose into W. And in back propagation lecture, in probably whatever week was there, one numerical problem was based on this particular concept. So they have changed the way of writing the variables, and then you have to calculate the output, that is y equals to x transpose into w. So you can write, there is no harm in it. So it is just the way that you represent your data. In generally in deep learning, we basically prefer to use the column vectors. It is a notion, but you can use the other way around, because you have the mathematical operation over there. You just take a transpose and then you can multiply. So there is no problem.
Okay, sir.
So the next question is, how can we prevent underfitting? So you have seen this particular question. So let me first ask you that what do you think that what would be the correct answer? Let's say option A. How many of you think that option A is the correct one? Option A is increase the number of data
Yes, sir.
samples.
Yes, sir. I feel option A is also a correct answer.
Okay. And what could be other, what you are thinking that what would be the other one which is correct?
Sir, in the solution, B is given as an answer, increase the number of parameters. But I really have doubt about that approach.
So here lies the query that they have given option B, but most of us think that option A would be the correct option. Okay. So example first, and then I will go to the solution of this particular question. Uh, so any one of you can tell me that why you are thinking that option B is not the correct one? What is the issue with option B? Is it like another anomaly that we have seen in week 8 question, or there is some rationality behind option B is there?
So, sir, what I understood is option B, they are talking about making the overall network more complex. Yes, if we add more hidden layers, that is going to generalize the overall model well. But I just didn't feel that we can just simply increase the parameters because we might have a limited number of features.
Okay. So
Yes, sir. And I also
yeah,
think that
so
increasing the complexity may increase the computation cost. And option A seems more reachable kind of.
yeah. So the option A is partially correct. Let me first tell you It is not like option A cannot be the answer. Option A is partially correct. And option B is which is absolutely correct. And why I will tell you. But as because, for example, this particular question is MCQ, not an MSQ. So this is not an MSQ type of question. You might encounter MSQ type of question in the final examination. Probably, I'm not sure about that. That is multiple select question. So if it be a multiple select question, you would have actually ticked both option A and option B as the correct option. But as because this is a MCQ question, so you have to choose only one answer over here. So option D is the correct one. And let me tell you why option D is more prominent than option A. So in case of deep learning, we know that deep learning is a data hungry process. And underfitting whatever topics we are now talking about, let us consider we are basically focusing on deep architectures. And another question associated with this, that we had machine learning architectures which were much simpler than the deep learning architecture. For example, in case of SVM, you might have just very small amount of weight value. So we had seen that we just need to increase the margin. Such we need to increase the margin by optimizing the weights, and as well as there was a Lagrangian was also there, as because that was a constrained optimization. Now, these machine and another, let's say another machine learning classifier was there, that is KNN, K nearest neighborhood. Over there, you just calculate the distance between each of the samples, and then you take, let's say if you choose K equal to 3, neighborhood equal to 3, you just consider the lowest value of distance, and then you can see that the higher occurrence of which particular class is there. So you just label it to that particular class which has higher occurrence in the distance, as far as the distance value is concerned, minimum distance value is concerned. So machine learning models were fairly simple. So why do we need the CNN based architecture, and most importantly, why deep architectures? So that has some rationality, that why we need deep architectures, and why should we make the architecture of deep learning framework more complex in nature. If you see the papers, I hope as because this AlexNet, BGG16, everything has been covered. So you can just go and search some of the papers. For example, AlexNet and BGG16. So which one is more deeper out of AlexNet and BGG16, which is more deeper network? Anyone? In case of AlexNet, how many convolutional layer was there? Yeah, you just can check. I need answer from you. Okay, so
So
if
VGG
you,
is better. VGG is better, sir.
uh, I have not asked whether it is better or not. I have asked that whether which one is more deeper.
Deeper
Bet-
VGG is deeper because it uses the convolution kernels are smaller, and also it uses
deep,
the yeah.
deeper means something else. Deeper means the number of layer. For example, you have a architecture like this. This is your input. This is your output, and this is hidden layer 1. And deeper means like this. You have two hidden layers. It doesn't matter whether you have used bigger kernel or smaller kernel. It doesn't matter. The thing is that whether the number of hidden layers have been increased or not. By that you mean whether the model is deeper or not. So by that logic, whether AlexNet is deeper or VG16 is deeper. VGG16 is deeper. In case of AlexNet, you had how many convolution layers it had? If you can recall, otherwise I have to check. Five convolutional layers. 1, 2, 3, 4, 5. Yes, you have 5 convolutional layers. So 5 conv layers, and apart from that, you have max pooling layers, dropout, followed by that fully connected layer. Those are there, but 5 convolutional layers are there. In case of VGG16, you had 13 convolution layers. So now you can see there must be some rationality in AlexNet came probably 2016 or something. VGGNet came in probably 2017. Or I might be wrong, but AlexNet came first, then VGG16 came. So there must be some rationality that people actually are fond of making the network more bigger and bigger or more complex, so to say. Now let me show you another result. Let me show you another in result, and then I will ask that what is the inference that you get from this this particular result. So AlexNet. So AlexNet was doing classification, and all these AlexNet, VGG16, everyone were using the ImageNet dataset. ImageNet dataset. And this particular ImageNet dataset has 10 millions of data. So there is no scarcity of data is present over here. In case of ImageNet dataset, you have 10 millions of data. So now let us see the classification accuracy of both these models. So AlexNet top 1% accuracy, we can see that top 1 accuracy is 50%, 56%. So over here, the value is 56% top 1 accuracy. So you know what is top 1 accuracy, what is top 5 accuracy. Everything has been covered in these neural network lectures. So, and let's say VGG16. Yeah, so this is the correct one. So VGG16 validation top 1% accuracy is 70.894. So if you can verify from the paper itself as well, but 70.894. So within 1 year of difference from which AlexNet came. So after 1 year, VGG16 came, and we can see that there is substantial increment in the convolution layers. That means the model has become more deeper, and both these models were working on the same dataset, that is ImageNet dataset, and which has ample amount of data, 10 millions of data. There is no scarcity of data is present over there. The problem is quite open to all, so you can also just download. You can also check the dataset as well. For dataset information is there publicly. So this dataset has ample amount of data, so you don't have to think about this particular scenario. Increase the number of data samples. You have enough amount of samples over here for each of the classes. And when AlexNet came with 5 convolutional layer, it had accuracy value 56%. And with VGG16, you can see that the accuracy within 1 year and within increment of the convolutional layers almost, let's say, 1.5 times. So what there you can see there is a 20% increment in the accuracy value. There is 20% in almost 14% increment is there. 15% increment is there. 15% increment. So now can you refer something from this particular result? So you have ample amount of data over here. Your model has now become complex, and you can see that initially you are not able to extract good features, so-called good features. That is why your final accuracy was 56%. Now with the increment of the layers or the deeper, you make the model more deeper so as the complexity is now increased, and therefore you can see that you might obviously you are extracting good features from the input image, and that is why your accuracy has now increased by 15%. So can you infer anything from here, from this particular case study? So let me frame you the question as well. Let's say as you increase the number of layers, let's say you are increasing the number of layers. So what will happen with the number of parameters? So will it increase or decrease? What will happen?
Increase.
Yeah, it will increase number of parameters. And then what is happening from the result? Now refer to the result. Now you can see that when your model has become more deeper, now the capacity of the model to learn from the data has increased, and thereby you are getting a 15% increment in the accuracy. So therefore capacity of model increased, and therefore can you just make a comment whether you are learning something more efficient or not? So as your number of hidden layers is increased, so as the number of parameters have been increased. From the final accuracy, you can see that your capacity of the model has also increased, as because you are getting higher accuracy. Now my question is, from all these case study, can you comment that whether you are learning something more efficient from the data that you are feeding to the model? As you increase the number of layers, are you learning something more efficient?
Yes.
Yeah. So the answer is yes. And how you can say it is yes? It is from the results that you are seeing over here. Now the question is, underfitting is what? In case of underfitting means basically let's say you feed data into model, you are not able to capture anything from the data, and that is why let's say your accuracy goes drastically, it goes down. So that particular scenario is called underfitting, with at the condition at which you are not able to understand anything from the data. You can consider this particular scenario as, let's say this is scenario 1, this is scenario 2. Initially, you are extracting some features for which you are getting 56% accuracy. That means almost, let's say, let us consider it is 50% accuracy. So let's say this half probability is there. Either you classify it correctly, otherwise it will be misclassified. So that means still you are at a boundary that you are not able to understand some meaningful feature from any sort of any image. Now with 70% accuracy when came, now you can infer that okay, I might have some good features that I have learned from the bigger model, and that particular bigger model now helps me to understand the hidden representation or hidden information from the data, which basically refers that you are learning something efficient from the data itself, and therefore it tries to reduce the uh, efficacy of underfitting. That means you are getting something more generalized, which was not there in case of this 50% accuracy. Over there, you have two probabilities: either you classify or it will be misclassified. Now over here with 70% confidence, you can say that okay, whatever data will come, I will be able to classify the particular image with a 70% confidence. So indeed, increasing the number of parameter helps to helps the model in gaining more capacity, and therefore therefore it is able to extract more representation information from the data, which basically reduces the chance of underfitting. So option B, I think it seems to be clear now why option B could be a correct option. We are not at a position to say that it is the absolutely correct, rather than what option A is a partially correct. So let me just ask whether you guys are now agreed that option B could be a correct answer. It could be a correct answer. I'm not saying that it is absolutely correct. It could be a correct option. So are you agreeing with this particular argument or not?
No, sir. I still have a different opinion, and the reason is we can make the network as complex as deeper as we want, but if there is not sufficient data, then the network is not going to learn. So
Yeah.
what
So for
I thought
that,
was
now I can give you an example. For example, you can make your model more complex, and you have very less amount of data. You have. So at that particular condition, your query, it is a correct query. So your query is that we have very less amount of data, but your model is very complex. Will it be able to learn anything? That is the question, right?
yes, sir.
So you have read a learning mechanism that is called transfer learning. What happens in case of transfer learning? You have very lesser amount of data. In a data set, you have very lesser amount of data. What you do, you uh, you actually take the weights from a complex model, let's say a pre-trained model such as, let's say, BGG16. So this VG16 itself is very complex. Now just check whether all the points that you have raised are ticked here or not. So you are taking a pre-trained model which is complex enough. Let's say this is VGG16. So you have a complex model. You have very less amount of data. Let's say you have Pascal data. Now you have already read that transfer learning mechanism is there, in which you actually encounter the same situation. Using transfer learning, you may achieve higher accuracy. Why higher accuracy? Even though with very less amount of data, if you recall from the lecture, even though you have very less amount of data, over there, your complex model, if you just fine tune the model, your complex model is now able to extract good representations such that you will be able to classify the images efficiently. This is one scenario. For this particular problem, if this sort of problem comes, this could be one scenario by which you can tackle. Second scenario could be, in this week's lecture, you have seen that triplet loss. That triplet loss, when Professor PKV actually introduced triplet loss, you might have seen that we referred to a problem. Let's say you have a very small organization. So over there you will have very small amount of limited amount of data for face recognition. So you cannot train a very big complex model over there to get your classification done. But in deep learning, you have a new mechanism called one-shot learning. By using one-shot learning, you can classify the images efficiently. So that means even though you have very lesser amount of data, you have different techniques to tackle that particular problem. So even though you have very small amount of data, you have transfer learning mechanism, one-shot learning mechanism, which might help you in preventing this underfitting issue. But if your model is not in a position to learn anything from the data, it doesn't matter whether you increase the data. For example, you have a let's say you do a classification using, let's say 1 million. Initially, you were classifying using 100 data, and your model is very low parameter model. With this, you are getting, let's say, 20% accuracy. You cannot guarantee if you increase this 100 to 1 million, if your model is still having very low parameter, you cannot ensure that your model will be able to yield 90% accuracy as it is seen 10 millions of images. The main thing is that if a person is dumb, if you show 10 millions of examples, he or she might not be able to give you the correct result. He or she should have some sort of intelligence by which if you show the image, now it is able to adapt his or her intelligence, and then you can do the classification in more efficient way. So for this particular scenario that you have referred, you can use transfer learning mechanism, one-shot learning mechanism by which you can do the classification. And in case of one-shot learning, the definition of one-shot learning, if you have seen that one-shot learning is a learning mechanism in which you learn from a single image or a few number of images. That means from a single image also you can learn something and you can able to classify. And that you do using triplet loss, contrast triplet, etc. is there. But the main thing is that if your model is not intelligent enough, so-called, if it is not intelligent enough, then whatever you show 10 million of data, 100 million of data, it will not be able to give you perfect result. Your model should be intelligent enough, and how you can ensure that intelligence is there if you increase the hidden layers and so as the number of parameters. That is why option B is the correct option. So in case of option A, that is partially correct. You can increase the number of samples, but even though if you have very less amount of samples, we already have seen how we can get good results out of the small amount of samples. So transfer learning mechanism is one such example.
Hello, sir.
Yes.
If you allow, I would like to extend this question. Like, if we have a limited amount of resources in the inferencing machine, for example, if we are implementing our model to an IoT device, then more complex.
Sorry. Can you please again frame the
Sure,
question?
sure. If we have inferencing device resources very less. For
Okay, so
example,
that means you are talking about the hardware requirement that you are asking,
yes,
right?
yes, yes, yes.
Yeah, so
Computation
that is
capabilities.
that
Yes.
is different thing. That is different thing. So hardware requirement, let's say, for example, I think you guys use ChatGPT. ChatGPT has 400 million parameters. But whenever you ask questions to ChatGPT, how fast it gives you the answer? It basically based on the fact that where you have deployed the model. If you are If you have deployed the model in cloud, then you have enough resources to do all the computation. If you are doing in a normal PC, it might take time, but it may be able to give you result. And let's say if you are doing in Arduino, which is a low-end processor, then obviously you cannot implement any of these networks, LXNet, VGGNet, whatever net is there, you cannot implement any of these models. But that is something else. That issue is something else that comes with some other problem. But over here, first our task is to reduce underfitting means you need to learn something. So for that matter, we are not at all bothered about whether we are working on high resource based machine, low resource based machine. Our aim is not to over here. Aim is not like to talk about the hardware capability or something like that. That is an issue, but over here we are not addressing all those things.
Okay, sir. Sorry.
So to answer that, you can check. So you have seen these AlexNet, VGGNet, all these nets you have seen. There is another network. Whatever question you have asked, that question is answered in this paper, mobile net. So the problem was same that you have told. With time, with let's say 2015, 2016, and let's say 2000, probably 2018, there was a paper called DenseNet 101. So they were also the winner of ICLSV challenge that you have already seen. So the very large image recognition challenge that was there. So in DenseNet, they have probably 150 million parameter. So now you can see that with the increase in time, the papers that came into picture, AlexNet, VGNet, DenseNet, the number of parameters was hugely increasing. Now you can train this model for a month if you have enough amount of resources. Anyway, if you just try to download this particular data set, you can think that you can get an idea that 10 millions of data, how much space or how much internet speed you need. So space requirement is a prominent issue over there to store the image itself. And on top of that, you need to build a deep learning model. So that is pretty space consuming thing. Now, as we have seen the problem that with the increase in the layer, so over here DenseNet 101 signifies that it has 101 number of hidden layers. So BGG16 had 13 convolution layers, so total hidden layer was 16. In 2018, people came with 101 hidden layer network. So in 2019, probably mobile net people, they actually argued the thing that let's say we want to these CNNs are used for face recognition. So face recognition, where can we do face recognition? Let's say in our mobile phone, when we actually unlock our mobile phone, we have face unlock option. So you cannot deploy this DenseNet or VGG16, this highly memory consuming architecture into the mobile, and you will see that if you deploy that particular deep learning model while unlocking your mobile phone, it will take 5 to 10 minutes just to unlock the mobile. So in 2019, people came with a new solution that is called mobile net. So mobile net basically means that the neural network can be now deployed in mobile phone, smartphone, which is of low compute, or less hardware, which has lesser amount of hardware for computation. So mobile phone could be one such example. So people actually created a new convolution that is called depth-wise separable convolution. This depth-wise separable convolution that is different from standard convolution that we have seen in this particular lecture series. We'll not talk about depth-wise convolution in the lectures as well. But as you have just asked this particular question, if you see this particular paper, will your question will be answered over there. They created a new convolution which reduces the computation almost 16 to 17 times, which is there in case of simple convolution. By using this particular convolution method, now your number of parameter will be drastically reduced, computation will be reduced, and then if you have a low resource based microprocessor or a mobile phone, then you can employ your model over there. So you can check this particular paper, but in this whole course, we'll not talk about mobile net deploy separate convolution.
Thank you.
So this deep learning course, you can see that it is basically based on the recent advancements. So all these networks, they are not like very old. Just a decade before only these things have came, and whatever question you'll ask, you'll see that most of the questions have been answered in the recent papers. So that is why I am referring to this paper. So it might seem quite intriguing that the solutions are, but to get the solutions you need to read paper, but that is what you have to do, because these advancements that are there, these are also quite new. This triplet loss and all contrastive learning, these are also quite new.
Yes, sir. Yeah, that's not a problem. Thank you, sir.
Okay. So the next question is, how do we generally calculate mean and variance during testing? So already we have seen that in case of batch normalization. So oh yeah, over here in case of training, we have this particular mechanism is there to calculate the means. So what there you calculate based on the number of batch and spatial dimension, that is W and H. So you take the normalization or the mean calculation based on the spatial dimension and batch information. And in case of testing, you do averaging of this mu and sigma. And this average, you can take simple average that we do sigma 1 plus sigma 2 plus sigma 3 dot sigma 100 divided by 100. So that is normal average. Another average you can also employ that basically most of the papers use, that is called exponentially decaying average. Have you ever heard this particular term, exponentially decaying average?
Yes, sir.
Yeah, so you have seen this particular exponentially decaying average in RMS prop. So over there was a term RT, which was basically helping in adaptively scaling the gradient in different dimensions. So over there you have seen this particular term, that is exponentially decaying average. So either you can take simple average or you can take exponentially decaying average. In basically batch normalization technique, in most of the papers, they basically use exponentially decaying average technique. So initially people came with simple averaging. Later on, people talk about exponentially decaying average techniques to do the test time calculation. Okay. So let us see the image, the options. So batch normalization is not required during testing. So this is false. In case of batch normalization, we do use at the time of testing, and we have different type of calculation over there. So that is basically the uh, exponentially decaying average based on the mu and sigma that you have evaluated in the training phase. So these mu and sigma that you have evaluated in training phase, that is also known as estimated statistics. So again, if you want to see the all terminologies, so over here I am telling you the terminologies from the paper itself. So you can see the batch normalization paper, and then you can again refer to all these terminologies. So this mu and sigma that you have collected in training phase, you are taking average on all whatever you are doing. So that particular average or that particular mean and sigma, those are called estimated statistics. So now let us see. So option A is incorrect. Mean and variance based on test image. So that is we are not doing this. We already have told you that over here in the test image, you can see that yellowish image was there. We could have extracted mean and sigma from this particular yellowish flower image. However, if we do so, it will be highly differing from the images that we have seen in case of training phase. So that is why we'll be using the estimated statistics at the time of testing also. So therefore, we are not calculating mean and variance based on the test image. So this is also wrong. And option C is estimated mean and variance statistics during training. So we are using this. So how do we calculate the mean and variance during testing? So we are basically referring to the mean and variance that we have estimated during training. So that we have already talked about. So option C is the correct one. Okay. So the next question is, what is the advantage of dropout? So dropout basically helps you to reduce overfitting. And this is a sort of regularization technique. Why this is a regularization technique? This is because let's say you have n number of input neurons are there. By using dropout, you are penalizing the activations randomly. In each of the epoch, this penalization will be random. For example, in epoch number 1, these two are penalized. In epoch number, let's say 2, these two are penalized. So in each and every epoch, the location at which the penalization will happen, that will differ, and therefore the rest of the neurons will try to learn efficient information from the data that is being passed through the MLP or the CNN architectures. So over there, as because we are penalizing the activations over here in the neurons, and we are trying to capture more information, more sophisticated information from the rest of the neurons that is present in the network at the time of training the model. So this acts as a regularizing feature, regularizing technique. So over there, it is also a regularization. It is also a regularization. And another uh, uh, outcome of these two. So we are doing regularization. We are reducing overfitting. So in what is overfitting? Overfitting is basically, if I just talk about in terms of accuracy, let's say this is your training accuracy, almost 100%, and this is your validation accuracy. Let's say it is around 50%. So you can see there is a huge gap in between the training and validation card. So this phenomena is called overfitting. Now, in case of overfitting, you can see that your testing accuracy or the validation accuracy has dropped down significantly. By using regularization, by using dropout regularization, what you are ensuring is that your model is now able to extract good information as from the data that is being passed through the model, with the notion that in each and every epoch, the activation will be penalized from different sort of neurons that is not quite known, that is random in nature, and that will ensure that whatever neuron is there, that will be able to capture maximum information or robust information from the data. So which will later on actually reduce the overfitting issue. And overfitting, we can see that overfitting issue, if it is reduced, that means this gap will be reduced. And this gap will be reduced, that means the accuracy will be improved. Overfitting means there will be a huge gap in between training and validation. When overfitting will be improved by using dropout, that means the curve, the validation curve will be now shifted from this point to this point, and therefore the gap in between these two will be significantly dropped down, and therefore the accuracy will be improved. From the figure itself, we can observe that. So it is a regularization technique. It prevents overfitting. It improves accuracy, and therefore option D is the correct answer for this particular question. Okay. So which is true? So you already have seen the question. So let me just ask you that batch normalization technique normalizes over which entities? We already have seen in this particular slide. We already have seen, but let's just again discuss that on which entities the batch normalization technique actually normalizes. So over here you can refer to the options as well. So what are the two entities on which batch normalization technique works?
Spatial and batch.
Yeah, spatial and batch. So over here we already have shown you that if this is height and width of the tensor, so we have to consider this whole tensor, this whole tensor, and we have to add all the values over this W and H. So that is what we are doing over here. And at the same time, in case of batch normalization, we first what we do, we accumulate all the outputs of the tensor uh, into a channel wise representation. For example, channel 0 is accumulated over here, then channel 1 is accumulated over here from all these outputs. So that means this channel information is fixed. And that is why we can see that this capital C still holds over here. So this also I have already told you that how we are basically writing XICJK. So this C is fixed as because we are calculating the mean and variance for this channel 0, for this channel 1 separately. So that means this channel information will be fixed. What is varying? It is the spatial width and the number of batch. So this N is basically refers to the batch. So therefore spatial information and batch information. And similarly, what about the layer normalization? In case of layer normalization, what are the entities that on which it works? So this is layer normalization. So this mechanism is layer normalization.
Spatial and channels.
Yeah. So over here, the mean and sigma, mu and sigma. So let's say this is batch 1, batch 2, 3, and 4. Over here, you can see this batch is fixed. For this whole batch, you are calculating mu and sigma. For this whole thing, you are calculating mu and sigma. So over there, we can see that this batch information or this N is fixed. And that is why while calculating this, you can see that capital N is not changing. What is changing is this spatial width. These two correspond to the spatial width and height. And this C basically tells you the channel dimension. So you can infer from here also. So you can see this is the height. Let's say this is width and this is height. And these are the channels. So now you can see you are calculating all the summations over. First summation will be happening over here. Then second summation will be happening on channel 1, third summation will be happening on channel 3. Likewise, you have done all the summations over here, and then you just divide it by C. Then you will get a average. And that is what you can observe from here as well. You are also adding the channel number, as because you can see the channel 0, channel 1, 2, 3, 4. You are doing this average operation on this whole 4 channels. So that is why layer normalization is dependent on channel dimension, spatial width and height. So now let us see which is the correct one. So batch normalization normalizes over spatial and channel. So this is wrong. Then layer normalization over spatial and channel, and batch normalization over spatial and batch. So option A is the correct. So any query on this? Yeah, any query on this particular question? So I hope there is no query, so I can proceed with the next one. So the next question states that 1 second. Sorry for the interruption. Oh, so the question was, which one of the following is a regularization method that includes sparsity among the trained weights? So I hope you have answered this particular question. So just tell me that which is the correct answer and what is the reason behind that, which we have picked as a correct answer, and what is the reason? Is it L1, L2, or both? Have you answered this particular question? So the question is which basically, okay. Sophia, probably she has answered. So what is the reason? So first of all, what is the correct answer for this particular question? Sophia, I can see you have raised hand. Anyone? If you have.
Sir, we can't see the question. I think there is a screen behind.
Okay, this is the question.
Yeah.
So,
L1 will be the one introduces sparsity among the training weights.
and how it introduces sparsity?
Yeah, because it actually, like in a, I think that when you see the response, basically it is actually an what do you call that? It is a diamond shaped, right? Like it is a. So basically, it actually instead of uh, predicting the correct value, it actually imposes a lot of zeros in the.
Yeah, that is what sparsity means, but how? So is there any mathematical intervention is there, or
Sir,
yes?
actually L1 norm is a difference and the L2 norm is the square and then sum of squares and then under root. So due to this, the term will not be, the terms will be positive terms and will not be any negative term, while when
So
we are taking the
you
difference and model.
one second. You are talking about L1 node, right? That means
Yes.
x1 minus x2.
X2, yes. Sir.
Yeah. So this is something else. This is norm, and this is regularizer. So L1 means lasso regularizer. L2 means reach regularizer. So L1 norm is different. Norm you basically use uh, uh, for distance measure, matlab, in case of distance measurement, similarity measurement, for those type of applications, you use this L1 norm, but this is not norm. This is regularizer.
Okay, sir. Sorry.
Yeah, there's nothing to be sorry about it. So uh, we have seen where this regularizer term is introduced in loss. So loss is dependent on what? It is dependent on the weights. So we have seen in case of MSC loss, we have seen the categorical cross entropy loss, binary cross entropy loss, different loss functions we have seen, and we actually we have seen that we take the gradient of L, which is a function of W, and we try to optimize these weights, and that is why we take differentiation with respect to W itself. So that is del LW of del W. So that is what we do in case of loss. Now we have seen loss term. It is comprised with data loss plus regularizer. Okay. So over here, it is L1 regularizer that basically gives you sparsity. Please don't mind the spelling mistakes. Deliberately I'm doing spelling mistake in regularizer. So this is LW or the loss function. So now let us consider this how we can say that the weights have been we make sparsity on the weight updation using L1 regularizer. So the question is which regularization method includes sparsity among the trained weights? So there must be something related with the weight updation technique. In the weight updation technique, we know that this is the equation for gradient descent rule. This is LW. Now, here we have written this LW. Now let us write it in a more concrete fashion. So let us consider data loss is G of W and this is L1 regularizer. Can any one of you tell me that what is the formulation of L1 regularizer? What is the formulation of L1 regularizer? It is similar to L1 norm, but it is not exactly what L1 norm looks like. L1 basically refers to absolute value. Okay. So therefore, we are taking L1 regularization to do sparsification of the weights. So therefore, L1 regularizer of weight. So this is what your loss function looks like. So this is the data loss and this is the loss due to the L1 regularizer or the L1 factor. Even in a more concrete fashion, if I write it, what you will be able to see in the papers, that is with regularizer, there is a constant term is also associated, which basically this lambda term basically tells you the strength of regularization technique, strength of regularizer. And then you can take summation of I equal to 1 to n, whatever number of weights you have, and then you can write W of I. So LW. So this will give you the flavor of matrix representation. So W of I, you can see that you have a number of weight values. So therefore you can arrange it in W1, W2 like that in that particular fashion, matrix fashion or vector fashion. Okay. Now let us do the grad L of W. So if I take gradient, so it will be G dash of W. So this is basically the data loss differentiation with respect to W or the weight. And over here, what will be the differentiation output? Over here, what will be the differentiation output? Yeah, in this particular mathematical expression, if I just take differentiation with respect to W itself, so what will be the output?
Lambda.
No. It would be lambda if I would have write it like this. But over here I have mod. This is mod. So what happens if I take mod of W and then we take differentiation? What happens? let us see the graph of mod W. So this is mod W and this is W. So now tell me what will be the differentiation output. So what is the definition of mod W? Is W when W is greater than 0, it is minus W. Sorry. Is also W only when it is over here. Right. So that means if you put, let's say, -1, then also you get 1 over here. You put 1 also, mod output will be 1. So that is why, let's say, if it is -1, then also it is over here. If it is 1, then also it is over here. So this is 1. Okay. So what happens if I take differentiation? Yes, anyone?
Sir, it will be 0 only, right, sir?
How?
Because this the differentiation is with respect to W, but you are taking mod of W, so which is basically an scalar value, right? It is the.
So let's say let for the positive side it is W only. Whatever I put here, I will get the same thing over here. So let us just it's just like ReLU. The positive half side, it just looks like ReLU. So if I take differentiation, so what will be the output for the positive half side?
Will be constant. It will be constant.
Yeah, what will be the value?
One.
Yeah, 1. So you will be doing dW by dW, and therefore it would be 1. Isn't it? Yes. Is there any confusion is there, or I can proceed? So for this particular,
if it is no, I think the modulus is confusing, sir. Like if you differentiate the mod of W with respect
this
to W, then how can, like, if it is a plain W, that's fine. But if you are taking mod and then you are taking differentiation, that's
mod W, first you tell me the definition of mod W. What is the definition of mod W?
Positive.
Yeah, so whatever value you put, you will get the positive output. Right. For example, if you put -2, then also you will get 2. If you put 2, then also you will get 2. And what will be the shape of mod W? What will be the shape of mod W if I just try to plot the mod W?
Linear.
Linear. So in this direction, it will be like this. And what will happen in the opposite direction?
Will still be same.
Still the same. It would be like this, right?
Yeah.
Yeah. Okay. So let me don't write in terms of differentiation equation. So differentiation means you are calculating slope, right? So if I take slope on this particular direction, so this is 0.0, this is 0.1, and if I put mod of 1, the output will be 1. So y value is also 1 only. So if I take slope y2 minus y1 divided by x2 minus x1. So y2 is 1 minus 0. And then again x2 is 1, 1 minus 0. So 1. So that means over here dy by dx is equals to 1 for the positive side. What about the negative side? Do the same thing, y2 minus y1, x2 minus x1. So in case of y2, in case of x2 is minus 1. So for that you get y2 is equals to 1, right? So you tell me what will be the computation over here, dy by dx. Yes, anyone? For the negative half side, now for this particular panel, I'm doing the slope calculation. Slope calculation is equals to the derivative. So
Sir, it will be 1 minus 0 divided by minus 1 minus 0.
so it will be minus 1. So therefore, you can see that if this was the mod W representation, the derivative is like this, plus 1 minus 1. Is it okay now? If I do d of mod W divided by dw.
So is that sin x?
Sin means SG and X. SG and X you are talking now.
Yeah.
So this is called signum of X. So this function is a signum function. So over there, so the main thing was that if you have positive value of W, so your derivative will be plus 1. If you have negative value of W, your derivative will be minus 1. So as from the figure itself, you can refer. In positive value, you get the positive thing, and in the negative here, you get the negative slope. So therefore minus 1. And that is what I also have proved over here, that if you do the slope calculation, you will get the same thing. So for the positive half, the dy dx will give you plus 1. For the negative half, the dy dx will give you minus 1. Okay, so till this point, it is like if I take the, I was taking the differentiation, so it is lambda into signum of W. Fine, till this point, I hope there is no issue. So now we have calculated the gradient of the loss. So now let us do the weight updation. Wn plus 1, it is now Wn minus delta WLW. So this becomes Wn minus first term is basically this G dashed of N, which comes from the data loss part. So that is G dashed of W. And let me just first write it in term in within parenthesis, and then I will, and then lambda into signum of W. Now, in case of signum of W, you have seen there will be two cases. One case would be that if W is positive, if W is negative, and if W is 0 also, then you can say that signum of 0 is signum of 0. Even though there are some finite rules are there, but let us not talk about that. Let us consider signum of 0 is 0. Okay. So first case would be if W is greater than 0. Then what would happen? Wn plus 1 is equals to Wn minus G dashed of W. And what will be the value of this particular thing if W is greater than 0? If W is greater than 0, what will be the value, overall value over here?
Lambda plus.
Lambda. Yeah. So plus lambda. If I just break open the bracket over here, so it would be minus lambda. I hope this is fine. Now you can see that you had an initial weight and now you are subtracting two things from this weight value. That means this weight value is reducing. And you can see that you are doing this particular thing in a recursive fashion. So for iteration 1 you are doing, then iteration 2, 3, up till how many number of iteration you have, till that particular iteration you will be doing the same thing. And you can see every time you do this operation, you can see that Wn is reduced from the value is now shrinking. As you can see that two terms have been negated from W. So therefore value is reducing or it is shrinking. And as you go along the number of iteration, you will see that most of the weight values will be highly shrinked or reduced, and which also signifies that most of the value will tend to 0. Is it fine?
Yes, sir.
So that is why you can say that your L1 regularizer basically tries to ensure that most of the weight value that basically the network learns, it tries to reduce the value or shrink down the value to 0. And adding in a matrix, as because you will not have a single weight, you will have multiple number of weight entries, as we have seen from our previous lectures as well. And in a matrix, if you introduce more and more 0, so that is what is called sparsity. And that is why you can see that L1 regularizer basically tries to incorporate this sparsity operation. If you have any query on this particular question, you can tell me. Otherwise, I will proceed with the next one.
Sir, can you also quickly explain L2, how L2 is going to behave?
Yeah. So in case of L2, so first we have to see that what is the loss function, what changes are there in case of loss function. So GW is data loss, that is fixed. You can use binary cross entropy, categorical cross entropy, MSE, depending on whether you are having classification or regression task. Okay. Along with that, you have a regularizer term. So in this case, let us consider you have a L2 regularizer. And again, regularizer will be applied on the weight value. So L2 regularizer on the weight. So in case of L2 regularization, we have what is the equation, or what is the form of L2 regularizer? Anyone of you, if you can tell me. It has some similarity with L2 non, but it is not exactly what L2 non looks like. But it has some similarity. Sorry.
Modulus of W square.
Yeah. So over here you'll have a square. And again, if you have several number of weights, which you'll obviously have, you'll have n number of weights. So therefore you can take a summation over here. So n equals to 1 to, let's say, capital N. Or you can omit it as well, as because we'll do derivative entry wise. So you can omit that as well. But as far as mathematical notion is concerned, you can write it like this. So this is what L2 norm looks like. Now you do the same thing. You take the gradient. So del LW by del W is equals to. So over there, it will be G dashed of W or del G by del W over here. And what will be the output now? What will be the output? Yes. Anyone? Yeah, what will be the differentiation output over here? So this you can think of lambda into, directly you can think of Wi square. So what you are doing is basically you are first taking absolute and then you are taking square. So squaring the value or taking absolute and then squaring will give you the same thing. That means if you take minus 2, you do square and you take mod of -2 and you do square, you will get the same value, isn't it? So if it is to be lambda into wi square, what will be the differentiation output?
Two lambda W.
Yeah. So 2 lambda W. And I have removed this subscript I over here. You can consider, if you consider everything, so you can put I everywhere. Now again, let us go to the weight updation equation. So now Wn plus 1 Wn minus delta W LW over here. And you can again write it like over here Wn minus, so minus G dashed of N, and it is 2 lambda Wi. And now you can see that when Wi is greater than 0, let us take two cases when Wi, or you can just think from this particular also, this scenario also, that would not be an issue. Yeah, so you have Wn and now you are negating with this minus G dash W, that is fine. Now over here you can see that you are negating with a bigger term, and computationally it has been seen that most of the values over here either they will be of very small in nature. I'm talking about Wn plus 1, or they will be negated, of negative nature. So now over here you can see that this minus 2 lambda into W, initially it was lambda only. But over here you can see you are including the Wi weight value. You are multiplying with the regularizer component term, and along with that you are multiplying with 2 as well. So over here when you do the subtraction, you will get something which is negative. And therefore the L2 regularization, it tries to reduce, the main target is to reduce the value of weight, which also L1 also does. L1 also tries to reduce the value of weight, but it has been seen that numerically upon doing these things again and again, L1 norm basically tries to get you down to the 0 term. However, if you do the same, if you do this thing over here, most of the cases you will see the values will be reduced, but majority of the values may get to negative value. Either value will be very small or value will be negative. Some of the value may be 0 as well, but over here in case of L1 regularizer, most of the value will be 0. So it is computationally, you can take any sort of regression problem and then you do the computation. You will see that computationally it will show you that most of the value will be uh, 0 in case of L1 regularizer. However, in case of L2 regularizer, you will see that most of the values are tending to 0 but not equal to 0, or else they are negative in nature. So this is how you can see the operation. You have to take the equation, you have to write the equation, then you have to write the gradient, and then you do the gradient descent rule over here. So these problems we have seen previously as well, which is not the data augmentation technique. So random shuffling is not a data augmentation technique. Probably in the last class, I have shown you the simulation as well, that vertical flipping is just flipping it along this particular axis. Then horizontal flipping, you can do it like this. And so this is a augmentation technique. Random color jittering. So you have a 3-channel mask, 3-channel data, RGB image, and you apply a noise. So noise will also have 3 channel. So if you add noise with that, so image will be just noisy. But if you keep this eta value to be it is restricted, it is, let's say it is restricted between 0 to 1, you are putting a normalization factor, this eta over here. So in the last class I'd show you that you are getting the same image, but it was perturbed with salt and pepper noise kind of thing. So there was some sort of dot kind of noise where they are present in the updated image. So this is also augmentation technique. But random shuffling, for example, if this is an image and let's say this is there is a person is there, and random shuffling means you will be shuffling all the pixels here and there. For example, this head. Now this head part is now going over here. This leg part is now, let's say it is like this. This body part is now over here and the hand is over here. So you have randomly shuffled all the pixel locations. So now you can see that initially you had a image of a person. Now this doesn't seem to be anything rational. So therefore, this is not a augmentation technique, as because the augmented output or the output transformation output, that is not quite similar to the original image itself. So therefore, or not a good extrapolation. So augmentation is basically extrapolating the data. So while extrapolating the data, you are basically uh, tampering the information in the which was there in case of previously in the original data itself. So you can see that the data is tampered over here. So that is why this random shuffling is not the data augmentation. So in case of random sampling, output is totally tampered version of. So which of the following is true about model capacity? This model capacity we have elaborately discussed in our previous question, that if you increase the number of hidden layers, then the model will be more complex and so as its capacity will increase. So therefore, this is the correct answer. Learning rate has nothing to do with the model capacity. It basically ensures that how fast your optimization process will settle down, and dropout is, it's basically a regularizer term. So it adds regularization, but you cannot certainly say that it will increase the model capacity. It might increase the model capacity, but it has no prominent response on model capacity increment. So it is only the hidden layer. If you make the model more complex and complex, then only your model capacity will increase, as because then the model will be able to extract more and more information from the input data. Okay, so this question also we have seen in the previous class. So we have two training schedules, and training schedule 1 and training schedule 2. And we can see that in each of the training schedule, the mini batches which have been constructed using image 1, 2, 3, over here image 1, 4, 3. As because we can see that mini batch construction, the images inside the mini batch is what you call different. Therefore, their mu and sigma for this particular batch, for let's say mini batch 1, 1 and mini batch 1, 2. So this subscript are scheduled. Okay, so this schedule 1 I have subscripted over here. So mini batch 1, 2, you can see that you have a different image over here. So if you have a different image, so when you calculate this sigma and mu, you have seen from the equation itself. So for example, in case of batch normalization, you will be combining the channels from different set of outputs. So as your inputs are different, so therefore their outputs, the model outputs will also be different. So as the mu and sigma that will calculate using batch normalization technique, the statistics will also differ. And therefore, if the statistics is differing, then activation will also differ. So this we have seen in the previous live session as well. We have taken similar problem like that. So activation outputs corresponding image will different across training schedule 1 and training schedule 2. So which is obvious that your images are different in the schedule in the mini batch. If the images are different, then their outputs from the neural network will be different. Then on top of that, you will be calculating the batch normalization output. So as the outputs of the neural network itself is different, so therefore your mu and sigma, those will also be different. And if mu and sigma is different, so we'll be doing the batch normalization layered output x hat will be x minus mu by sigma. As these are differing, so therefore this x hat output will also differ. And therefore the activation outputs of the corresponding image from training schedule 1 and 2, they will also differ. So with this, we have covered the week 10 quiz part. So if you have any query on the quiz part that I have solved, you can tell me. Any query on these 10 questions? Okay. Is anyone? Okay, so I hope it's not the queries there. So you have been given a signal and you have been given a filter. Then you have to perform stride to transpose convolution, filter f to that of y. And what will be the signal y if we don't perform propping? Okay. So how do we calculate this transpose convolution? Anyone? How do we calculate transpose convolution?
Sir, we will take the transpose of that filter.
Yeah, so this is the signal and this is the filter. So you will get y0, y1, y2, y3. And you have to take stride 2. So then what will be the next location? If I take stride 2,
Y2.
from which location? Yeah, y2, yes.
Right.
Yeah, so it would be 1, 2, 3, 4. Okay, so it will give you y4, y5. Then again, you have to take stride 2. So it will come over here 1, 2, 3, 4. So you will get y5, so y6, y7. And then again, you have to come over here 1, 2, 3, 4. So it would be y8, y9. And then again, you have to do it like this 1, 2, 3, 4. So y9, y10, y11. So is this okay to all, or should I just explain again that how this transpose convolution is going? Is it okay?
Yes, sir.
Yeah. So now you can calculate. So the first output will be 1 into 5. So 5, right? So the second output will be how much?
2 into 5.
2 into 5, so 10 over here. So the third output will be, what will be
3
the
into 5 plus 4 into 1.
Yeah, so it would be 15 plus 4. So this will be 19. So we can see already you don't have to calculate the later terms as well. So they have given the option quite discriminating over here. So there's quite discretion. So option D is the correct answer from the first output itself. So in this way, if you just calculate all the responses, you will get this particular output over here. So I'm not doing the whole calculation over here. So you can do it. So for let's just do the last operation over here. So the last operation will be 4 multiplied with 1. So the output, last output will be 4. So that is what we can see over here. It will be 4. This one with 3. So again it will be 3 like this. So you can calculate all these values by your own as well. So we have calculated this these entities. Rest of the values you can calculate by yourself.
Sir, if we have to apply the cropping, in that case, which one we will exclude? So is it going to be like number of input features? That's the number of output. That's going to be cropping.
Actually, what we do in generally the question is framed. They have taken. You can see this is the even number of kernel elements, right? Generally, we take kernel elements of odd number. Like let's say you have x0, x1, x2, and x3, whatever may be in the signal. But in case of kernel, we take k0, k1, k2. Let me decrease this so that it will decay faster. Okay, so you will let's say strike 2 only. So it is strike 2. So it is k0, k1, and k2, and again with strike 2 it will be k0, k1, and k2. So the question is from which point we have to discard or we have to do the cropping. We have to start cropping. So over here it is output is y0, y1, and y2. We have to start taking the data from which the output is aligned with the center of the kernel. So the center of the kernel is what? This k1. So from this point we have to start considering the data. And similarly, so this is y3, y4, y4, y5, and y6. Now similarly, till what position we have to consider the data? Again, till the point where the last kernel center element is basically aligned with the output. So over here we can see that this is the final kernel position, and this k1 is aligned. This is the center element. This is the center element, and the center element is aligned with output y5. So we have to consider y1 to y5. Main thing is that center of the kernel we have to check alignment with output. So over here the center is aligned with y1, so we have to start considering from here. And where we have to stop? We have to stop at the same at the same notion where the center of the kernel element is basically aligned with the output. Is it fine?
And sir, you mean when the center is aligned, that's with respect to x2, right? Because that's where it's stopping.
With respect to the center is aligned with what position of the output? So this is the center. This is aligned with y1. So we have to uh, start considering the data from this point. Over here also the center corresponds to what output? The last position, the center corresponds to what output? This is y5. So that means Y5 is aligned with the last kernel position's center element. So that means we have to consider from Y1 to Y5.
Sir, my question is why we have to stop at Y5? Why not at Y3? There also the center is aligned, right? K0, K1, K2.
But you cannot stop at midway. You have to cover the whole signal. While
Correct,
doing
correct.
the
So,
while
yeah, so
doing the
basically we have to
convolution.
go.
Yes,
We
yes,
have to
please
go
go
all
ahead.
the way
Please
to
go ahead.
X2.
Yeah. You have to cover the whole signal. That is the thing.
Got it.
You have to cover the signal. Okay, so let me go to the next question. So the next question states that you have a deep CNN. So probably I'm rushing a bit. In a deep CNN architecture, you have a feature map and you are doing a max pull with kernel 2 by 2. So this is given below. Okay. So you are doing max pull with a kernel 2 by 2 and this is the feature map that you've been given. Now over here, after a few successive convolution layers, the feature map is again upsampled using max unpulling. So this thing you have seen probably in the lecture that in case of image segmentation, whatever image size we provide in the input while doing convolution and max pull, the size becomes reduced. It reduces, the size reduces due to subsampling procedure. Now at the output in the segmentation, image segmentation process, we need to get the same image dimension. So that is why we have to upsample the uh, um, there is a downsampled output. We need to upsample that thing to get the same image shape. So for that, we use two methods. One is direct upsampling. That is what you can see in case of FCN, fully convolutional neural network. In case of FCN, they use FCN 8, FCN 32, FCN 16. Different variations are there, and there are either you do a single step upsampling, you do two-step upsampling, three-step upsampling. You can do all these things. Otherwise, what you do is you use transpose convolution along with max unpulling operation. Now to do max unpulling operation, you basically need a variable that is called switch variable. What switch variable basically does? It basically tracks the location from which the maximum value is taken out. So over here we can now you'll see that what I have meant. So in case of doing the max pooling operation, let's say you place the kernel over here, 2 by 2 kernel you place over here. So what will be the maximum value over here?
50.
Yeah, it would be 50. And you can see that the 50 is taken from this particular position. So the switch variable will be of same shape. It will put a 1 over here. It will basically signify that it remembers that at this position the maximum value was present, and at the rest of the position it will be putting 0 only, because rest of the position there the highest value was not present. Again, let us put a mask over here. And now what is the highest value over here? The highest value is 10, right? And now where this switch variable will make an entry in this particular mask? So switch variable will make an entry at which the highest value was present. So the position of 10 is over here only. So therefore we'll get a 1 at this particular location. Similarly, now let us put the mask over here. What is the maximum value? The maximum value is 44. And the location of 44 is this one. So at 44, I will get 1, rest of the position I will get 0. And then again, you put a mask over here, the maximum value is 20. So over here it would be 1 over here, rest of the position will be 0. Okay. What will be the output of max unpooling layer? Now you got this is the switch variable location entries. This is the switch variable location entries. And over here you got a subsampled output. Now what you do, you put this subsampled output through max unpooling layer with switch variable. The output is y. You need to state that what will be the contents of y. So how can I fill y? You have the subsampled output. This is this one. What we have actually extracted. If you do the max pooling, so that is the output, or what we have written as subsampled output. Now the subsampled output is passed through max unpooling layer with switch variable. So what will be the output? How we can use this particular array and this particular array to write our y? In case of max pooling, what you are doing is for this from these 4 values, you are generating 1 value. From this 4 value, you are generating 1 value. And in case of max unpooling, you will be doing the just the opposite. That means from this 1 value, you will generate 4 values over here. Now you can see that you got a highest value and you have to do maximum unpooling. That means you have to extrapolate from a single value to 4 values. That is just the opposite of max pooling. And you have got the location at which you have to put that value. So over here, you can see that from this 50 from this particular value, you have to fill this particular array position. And now you can see that this particular array position is of this kind. So what will happen is that 50 will be multiplied with all these values. So as because there is 1, so it will get 50 into 1 will be 50 and rest of the position it will be 0, 0, 0. Similarly, you have 10 over here. Now from this 10, you will be creating this particular box. Right? Now for this 10, you will be multiplying 10 with all these values over here. So 0 into 10, 0 into 10, 0 into 10, 1 into 10. So that means 10, 0, 0, 0. So the main gist is that wherever 1 is there, you just have to see and then you have to put the value. So for the third case, it will map this 44 will be mapped over here for this particular mask. So over here 1 is written in this particular location. So 44, 0, 0, 0. And similarly for 20, this particular mask will be activated. Now in this mask, we can see that 1 is written in the last position. So 20 will be multiplied over here. So 20 into 1, we will get 20 and the rest of the position will get 0. So this is the output y. So any confusion?
No, sir.
Okay. So this is how you need to actually consider the switch variable first, and then you have to drop down the positional arguments. This is this one, and yeah, there are the options. So let us just match. So 50, 10, 50, 10, and 44 over here and 20 over here. So 44 and 20. So option A is the correct option for this question. Okay. So you will see that over here you see that there are two cases. One is you need to calculate the dice coefficient between A and B. Okay, so let me just write down the dice coefficient equation so you can calculate by yourself as well. So A into B, A plus B. So this is the dice coefficient value. You multiply these two things first, then all the elements will be added with each other. So I equals to 1 to 8. So the 1, 2, 3, 4. So sorry, not 8. So this is total 16 values will be there. And then over here it will be 1 to 8. It will be 1 to 8. So I hope you can calculate the values, right? Just take summation of all the entries in A, take summation in all the entries of these, that will give you this sum of this and sum of this. And for the numerator part, you multiply element wise, like 0.01 into 0.01. So 0.10 multiplied with 0.01. Then this will be multiplied with this. After doing multiplication, you take summation. And then you just put all the values according to the formulation, and then you'll get the dice coefficient. As because this dice coefficient is not covered in week 10, week 11 lecture, that is in week 12 probably. But I have seen some of the questions they have given from week dice coefficient as well. So you can use this particular enumeration, or you can see week 11, week 12 first lecture. So their dice coefficient is explained, and you can get the which answers to it. So if you have any queries, then I can answer. Otherwise, we can end the lecture here. Any query?
One question for the two-dimensional case, the one which we covered, deconvolution, the filter which we applied, that's not clear how for two-dimensional cases that is done.
Yeah, if I just show it in terms of in pen and paper, now it will be difficult. What you do, I will create a Python live script. Okay, so in that live script, I will share in my GitHub profile, right? Then you can just go there and you can see the thing. Otherwise, if I show it over here using masks, so it would be quite confusing, because in case of 1D, you can see that the contribution is coming from all the places. For example, at this particular place, the contribution coming from the adjacent places as well. So over here also, for example, in this case, contribution is coming from these two places. So in case of 2D, it is quite confusing to show in pen and paper. Otherwise, I will write a script, and from the script itself, you'll be able to understand that how the multiplications are going. Okay, so I will provide this script to you, and then you can see.
Sure, thank you.
Just remind me, I just put this query in the forum, so that if I will check the forum definitely. If I just forget about it, just write that query in the forum. I will do it and upload in my GitHub. So I think now we can stop the lecture here.
Thank you, sir.
Okay.